Okay, hi folks, this is the last in the videos from Unit 2, that's Quanta and Waves, and this one is on polarization. So again, we're going to the Calder Glen High School website, the Advanced Higher page. I'm going to past papers there, and then we are going to click on the link for Mr. Davies' interactive PDF of past papers. And when you open that, you'll see there's the polarization questions there. And if you click on any of those questions, the question will appear with the solution tagged onto the end of it. It's a wonderful document. Now, there's only 4 questions there on polarization. And so firstly, we're going to have a look at the 2020 paper, and that's question 11. Now, Mr. Davey calls this the 2020 paper, although you'll notice on the front of it, it says the 2021 assessment resource. And that's because this paper was written for 2020, but there were no exams that year, and then the paper was given to schools in 2021 so that they could use it in school for the alternative certification model. Anyway, we're going to have a look at question 11, and as usual, have a go at the question first and then come back once you've done that and you can see how we have worked through it. So here we go. A teacher sets up an experiment to determine Brewster's angle for perspex. The experimental setup is shown in figure 11a, and the lamp produces unpolarized light, and light from the lamp is reflected from the surface of the perspex and is viewed through the analyzer. And the position of the analyzer is set so that angle theta is equal to Brewster's angle IP. And the transmission axis of the analyzer is at right angles to the plane of polarization of light reflected from the surface of the perspex at Brewster's angle. And you should remember here that at Brewster's angle, the reflected light is 100% plane polarized, and if your analyzer is at right angles to that polarized light, then you will not see any reflected light or glare from the surface of the perspex. Now, I've got a great wee demo of this experiment, although I'm using water instead of perspex, but I'll put a link to it in the description. So for part A, we've to state what's meant by plane polarized light. Well, you should know that light's an electromagnetic wave, and it's got an electric field component and a magnetic field component. And it's only the electric field vector that undergoes the polarizing effect here. So the electric field vector is forced to oscillate in one plane only. And make sure you don't say direction there, make sure you say one plane only. B part 1, complete figure 11b to show the path of a ray of light that's refracted into the perspex. Well, at Brewster's angle, you should know that the angle between the refracted ray and the reflected ray is 90 degrees. And so carefully with a ruler, your refracted ray should be at right angles to the reflected ray. I'm going to draw a wee right angle symbol on it as well. And remember, the angle of the reflected ray is the same as the incident angle. Well, let's have a look at the marking instructions. So for part A, remember you've got to say the light's oscillating in a single plane. And for part B, then the refracted ray is at 90 degrees to the reflected ray. Just 1 mark each for both of them. Okay, 11 part B, part 2. Calculate Brewster's angle for perspex. So straight to your relationship sheet. N equals tan IP, where N is the refractive index of the material and IP is Brewster's angle for that material. And if you look up perspex on your datasheet, it's got a refractive index of 1.49. And if you do shift tan of 1.49 on your calculator, that gives you a Brewster's angle of 56.1 degrees. And I'm going to 3 significant figures there because the refractive index is to 3 significant figures. Part C, using the same apparatus, the analyzer's gradually moved as shown in figure 11c. And we have to describe how the brightness of the reflected light viewed through the analyzer changes when the analyzer is gradually moved from position A through Brewster's angle to position B. And remember, at Brewster's angle there will be no observed reflected light viewed through the analyzer. So at Brewster's angle, light is 100% plane polarized, and at angles below and above this, the light will only be partially plane polarized. So as the analyzer is moved from position A to B, the light will become dimmer and then become brighter again. Let's look at the MIs. That's part C. All you need to say here is that the reflected light becomes dimmer for 1 mark and then becomes brighter again. On the right hand side there says the response must not indicate a sudden change. So watch, you don't say there, it's bright at A It's bright at B and it's dim in between. Has to be mention of a gradual change between the two. Right, we're going to have a look at another paper. This one is not on Mr. Davies' interactive PDF yet. It was last year's paper, the 2023 paper, and we're going to have a look at the polarisation question. It was question 12. And right away you should be able to see the similarity with the last question. 12 part A, state what's meant by plane polarised light. So same answer as before, the electric field vector of the light oscillates in one plane only. Then part B, unpolarised monochromatic light is incident on a glass block of refractive index n at angle IP. This is shown in figure 12A. So we're at Brewster's angle again, and then we're told some of the light is refracted into the glass and the remaining light is reflected, and the reflected light is plane polarised. And we have to derive the relationship n equals tan IP, where IP is Brewster's angle. Well, our starting point here is that the reflected ray will be at an angle of IP to the normal because of the law of reflection. And therefore 180 minus 90 minus IP will be equal to the refracted angle, angle R. And simplifying that, R is equal to 90 minus IP. And then from Snell's law, N is equal to sine I over sine R. And because R is 90 minus IP, then that becomes sine IP over sine 90 minus IP. And the sine of 90 minus IP is equal to cos IP. And sine IP over cos IP is tan IP. And that's the relationship we're asked to derive. Let's have a look at it on the marking instructions. So part A, same answer as before, the electric field vector oscillates in one plane only. And part B, it's a 3 marker, so first mark for stating Snell's law, second mark for identifying that the refracted ray angle is equal to 90 minus IP, and the third mark for realising that sine of 90 minus IP is equal to cos IP. And don't forget to write the final line as stated in the question. Okay, 12 part C. Lovely picture of a tram. I hope it's an Edinburgh tram. Sunlight can be plane polarised when it's reflected from water, and a tram driver wears polarising sunglasses to reduce the glare from reflected sunlight. And after a rain shower, sunlight's reflected from the surface of a puddle of water towards the tram, and this is shown in figure 12B. And in part 1 we have to determine the angle theta at which the sunlight reflected from the water surface is plane polarised. Well, let's zoom in on that wee diagram, because there's no normal on the diagram, and let's put a normal on it. And IP, the Brewster's angle, is the angle between the normal and the incident ray, so let's put that on it as well. And the angle between the reflected ray and the normal will also be equal to IP. And what you have to realise here, and this is a bit sneaky, is that theta is equal to 90 minus IP. And then we use our Brewster's angle relationship, n equals tan IP, where n will be the refractive index of water. And water's got a refractive index of 1.33. And if you shift tan 1.33, that gives you a Brewster's angle of 53.1 degrees. And 90 minus 53.1 gives you a theta equal to 36.9 degrees. Part 2, by considering the transmission axis of the driver's sunglasses, explain why the sunglasses reduce glare from the puddle of water. Well, the sunglasses are acting like an analyzer, and the transmission axis of the sunglasses is perpendicular to the plane of polarisation of reflected light. Finally, part D, the tram driver observes a rainbow in the sky while still wearing polarising sunglasses, and the driver notices that both ends of the rainbow are bright, but the brightness gradually decreases towards the highest point of the rainbow. And we have to explain why the brightness of the rainbow varies as described. Well, the light from the rainbow must be polarised, and if you think about it, a rainbow forms when sunlight behind you reflects off of tiny water droplets in front of you. Now, if the ends of the rainbow near the ground are bright, then the plane of polarisation of the light of the rainbow must be the same as his sunglasses. But the plane of polarisation must gradually change from vertical to horizontal as you move up and follow the tangent to the curve of the rainbow's arc. What a lovely wee question. Let's have a look at the marking instructions. There's part D there. Light from the rainbow is plane polarised, but the plane of polarisation gradually changes from vertical to horizontal as you move up the arc of the rainbow. That's it for this video then. Not a lot of marks for polarisation, usually quite a short wee question. But next time we're going to start having a look at Unit 3, that's the wee short unit on electromagnetism. And we'll start that off by looking at Coulomb's law and charges moving in electric and magnetic fields. Look at all the questions on that stuff. Blimey, going to be busy. See you in the next one.